Now we come to Chapter 3, Module 6. In this module, we shall study Fredholm integral equation of second kind with square integrable kernel. We shall see that a square integrable kernel can be associated with degenerate kernel, so that the theory of Fredholm alternative can be applied in case of integral equation with square integrable kernel. Now we consider the Fredholm integral equation of second kind given by equation 3.87, where the kernel kxt and the forcing function fx are square integrable in the square AB cross AB and in the interval AB respectively. Now, what is a square integrable function? The functions kxt and fx are square integrable in the square AB cross AB and in the interval AB respectively, imply that integral a to b mod kxt square dx, this is finite for all t in the closed interval AB. Also, integral a to b mod kxt square dt, this is also finite for all x belonging to the closed interval AB, and double integral a to b mod kxt square dx dt, this is also finite, and integral a to b mod fx square dx is finite, with norm of k, which is called the L2 norm of the function kxt. It is defined as double integral mod kxt square dx dt whole to the power half. Now in this module we shall see that a degenerate kernel can be associated with square integrable kernel, so that Fredholm's theorem, that is theorem 3.1 to 3.3 stated in chapter 3 module 5 for integral equation with continuous kernel, also hold in the case of integral equation with square integrable kernel. Now the integral equation 3.87, this integral equation with square integrable kernel and forcing function can be solved by applying the method of successive approximations to obtain its unique solution, provided lambda satisfies the condition given by 3.88. This condition has been derived in the previous module, that is chapter 3 module 5, while obtaining the Neumann series solution for Fredholm integral equation of second kind with continuous kernel and forcing function. It is important to note here that in case of Fredholm integral equation of second kind with square integrable kernel and forcing function, the unique solution can be obtained even if either or both endpoints of the interval AB in which the integral equation is defined are infinite, provided the condition 3.88 is satisfied. Next, we consider few examples of square integrable kernel. In example 1, show that the integral equation phi x equal to fx plus lambda integral 0 to 1 t into minimum of x and t phi t dt, x lying in the range 0 to 1, has unique solution if mod lambda satisfies the condition mod lambda less than 3 root 5 by 2. Now, the kernel of this integral equation is t multiplied by minimum of x and t. So, we break the interval 0 to 1 of the integral in this given integral equation as 0 to x plus x to 1. In the integral 0 to x, minimum between x and t is t. So, for t less than x, kernel kxt equal to t square, and from integral x to 1, t is greater than x, so that minimum of x and t is x. So, kernel kxt is equal to xt for x less than equal to t. Now, the unique solution of this integral equation will exist if the condition 3.88, that is mod lambda into norm of k2 is less than 1. So, we find the norm of k2. This is given by norm of k2 square is double integral mod kxt square dt dx. We break the t integral, that is inner integral, into 0 to x and x to 1, so that in place of the integral 0 to x, we replace this kxt square by t square, and in the second integral where t is greater than x, we replace the kernel kxt by xt, so that this can be simplified to obtain norm of k2 equal to 2 by 3 root 5. Therefore, the condition for existence of unique solution is given by mod lambda into norm of k2, that is mod lambda into 2 by 3 root 5 should be less than 1, that is lambda should be less than 3 root 5 by 2. Again, we come to example 2. Verify that the integral equation phi x minus lambda integral 0 to 1 minus maximum of x and t into phi t dt equal to fx, x lying in the interval 0 to 1, in which fx is a square integrable function, and this integral equation has unique solution if mod lambda is less than root over 6. Here also we break this integral 0 to 1 as 0 to x and x to 1, and we see that the kernel kxt, which is given by 1 minus maximum of x and t, is equal to 1 minus x for t less than x and 1 minus t for x less than equal to t. So, in this case, the solution, that is the unique solution, will exist if mod lambda into norm k2 is less than 1. Now, we calculate norm of k2. Like in previous example, we calculate this norm of k2 as, that is norm of k2 square as 1/6, so that norm of k2 is equal to 1 by 6. Therefore, the condition for existence of unique solution is given by mod lambda into norm of k2 is less than 1. So, that is mod lambda into 1 by root over 6 less than 1, which gives mod lambda less than root over 6. Now, we will mention some important notions regarding the square integrable functions. Here we consider the space omega of all continuous square integrable complex valued function gx of real variable x defined in the finite interval AB. First we come to observation given by remark 1. If phi x and psi x are two functions in omega, then their inner product is defined by integral a to b phi x into psi bar x dx, and this is denoted by first bracket phi psi first bracket closed as given in equation 3.89, and bar as before denotes the complex conjugate. We now mention few properties of inner product. First property is that inner product of phi and psi is equal to inner product of psi and phi bar, that is complex conjugate. Second property is the linearity property as given in number 2. Third property is that if lambda is any complex constant, then inner product of lambda phi and psi is equal to lambda into inner product of phi and psi, and also phi and lambda psi, their inner product is equal to lambda bar into inner product of phi and psi. Fourth property is that inner product of phi and phi is greater than equal to 0, and it is equal to 0 if and only if phi is equal to 0. Number 5 is that inner product of phi and psi, if it is equal to 0, then we say that the functions phi and psi are orthogonal to one another. The sixth property is that the positive number norm of phi, that is equal to square root of inner product of phi and phi, and this is called the norm of phi. Seventh property is that the mod of inner product of phi and psi is less than equal to norm of phi into norm of psi, and this is Schwarz inequality. And eighth property is the triangle inequality. Next we come to observation 2, that is given in remark 2. A set of functions phi I ranges from infinity, is said to be orthonormal set if the inner product of phi I and phi j equal to delta ij as given by equation 3.90, where delta ij is the Kronecker delta. Observation 3 given by remark 3 is a given orthonormal set of functions in the closed interval AB is said to be complete if the only function which is orthogonal to all members of given orthonormal set is the null function, that is the function which is 0 in the closed interval AB except at a finite number of points. Now we come to the fourth observation, which is given as remark 4. Every square integrable function phi belonging to omega can be expanded in Fourier series in terms of complete orthonormal set phi n x of functions given by phi x equal to summation n equal to 1 to infinity Cn phi n x as given in equation 3.91, where the Fourier coefficients Cn's are given by Cn equal to inner product of phi and phi n, that is equal to integral a to b phi x into phi n bar x dx as given in equation 3.92. Next we come to observation 5, which is given by remark 5. If capital K is an integral operator defined by capital K phi x equal to integral a to b kx t phi t dt, then its adjoint operator K star is defined by K star phi x equal to integral a to b k tx bar into phi t dt as given by equation 3.93. Moreover, if K star equal to K, then we call the operator capital K as self-adjoint. Next we come to theorem 3.4. Here we have to prove that inner product of K phi and psi is equal to inner product of phi K star psi. For proof, we start with the left hand side, that is the inner product of K phi and psi, and that is equal to, according to definition of inner product, integral a to b k phi t psi bar t dt, and that is equal to, we in this place we expand k phi t and write double integral a to b psi bar t dt integral a to b k ts phi s ds. Now we interchange the order of integration so that S integral is the outer integral and T integral is the inner integral, and we get integral a to b phi s ds integral a to b k t s psi bar t dt. This inner integral can be rewritten and we get integral a to b phi s ds integral a to b k bar ts psi t dt whole bar, so that the inner integral can be written as k star psi s bar, where k star is the adjoint operator of capital K, so that we get this is equal to integral a to b phi s into k star psi s bar ds, which is the inner product of phi and k star psi. So this theorem is proved. Now we come to remark 6. The value of lambda for which the homogeneous integral equation given by equation 3.95, that is I minus lambda capital K phi equal to 0, possesses non-trivial solution phi equal to phi lambda x, are called characteristic values or sometimes called eigenvalues of the operator capital K, and the corresponding functions phi lambda are called the characteristic functions or sometimes called the eigenfunctions. Now we come to theorem 3.5. If phi is a characteristic function of capital K for characteristic value lambda and psi is the characteristic function of the adjoint operator K star for characteristic value mu bar, and if mu is not equal to lambda, then phi is orthogonal to psi. That is, the inner product of phi and psi is equal to 0. We have to prove this. For proof, we see that phi is the characteristic function of the integral operator K for characteristic value lambda. That means phi satisfies phi minus lambda capital K phi equal to 0. Similarly, psi is the characteristic function of adjoint operator K star for characteristic value mu bar. Then psi satisfies psi minus mu bar K star psi equal to 0. Now we consider the inner product of phi and psi. So instead of phi, we can write phi equal to lambda K phi. So that inner product of phi and psi is equal to the inner product of lambda capital K phi and psi. And by the property of inner product, we can write this as lambda into inner product of K phi and psi as given by equation 3.97. We again consider the inner product of phi and psi, and instead of psi we can write psi equal to mu bar K star psi. So that inner product of phi and psi is equal to inner product of phi and mu bar K star psi, and by property of inner product, if I take out mu bar, then we get mu into inner product of K phi and psi as given by equation 3.98. Now we multiply equation 3.97 by mu and equation 3.98 by lambda, and we take the difference to get lambda minus mu into inner product of phi and psi equal to 0. Since we have assumed that lambda is not equal to mu, therefore the inner product of phi and psi equal to 0. So far we have studied various results concerning the inner products of square integrable functions. Now we shall see how a degenerate kernel can be associated with square integrable kernel of Fredholm integral equation of second kind. Now, if the kernel kxt is such that kxt equal to k bar tx, then we say that the kernel is symmetric, and the corresponding integral equation I minus lambda capital K phi equal to f is called symmetric integral equation. Next we come to theorem 3.6. If k is a linear integral operator from space omega of all continuous square integrable functions defined in the closed interval ab to itself, and if there exists a finite complete orthonormal basis of square integrable functions phi 1x, phi 2x, etc. up to phi capital Nx spanning the range of capital K, then we say that the operator capital K is a finite rank. If capital N is the rank of the operator capital K, then we have the result that capital K phi x equal to integral a to b summation n equal to 1 to capital N phi nx psi nt into phi t dt as given by equation 3.99, where psi ix are square integrable functions in omega. Now we have to prove this result given by equation 3.99. Capital K is a linear integral operator which is defined by equation 3.100, where phi x, k phi x and small k xt are all square integrable functions which belong to omega. Also, since the orthonormal basis functions phi I equal to 1 to capital N, span the range of capital K, so we can expand the square integrable function k phi x as summation n equal to 1 to capital N inner product of k phi n into phi nx as given by equation 3.101. Now, if I expand this inner product and write it in integral form, this capital K phi x is equal to summation small n equal to 1 to capital N integral a to b k phi u into phi n u bar du into phi nx. Again, we expand this integral operator capital K operating over phi u, so that we get k phi x equal to summation n equal to 1 to n integral a to b k u t phi t dt into phi bar n u du into phi nx. This can be rearranged so that we get k phi x equal to integral a to b, the summation goes inside, summation small n equal to capital N into integral a to b k u t phi n bar u du into phi nx, whole thing is multiplied by phi t dt. Now, we write the term in the first bracket of this expression, that is integral a to b k u t phi n bar u du as psi n t, which is given by 3.102, so that k phi x becomes equal to integral a to b summation phi n x into psi n t phi t dt as given by equation 3.103. So, if I compare equation 3.103, that is k phi x equal to this, with the equation 3.100, that is k phi x equal to integral k x t phi t dt, then we can observe that this k x t is given by summation n equal to 1 to capital N phi nx into psi nt as given by equation 3.104, except for a finite number of points in AB. So, we can observe that an integral operator of finite rank has degenerate kernel associated with it. Hence, the Fredholm theorems 3.1 to 3.3, which holds for Fredholm integral equation of second kind with continuous kernel, described in chapter 3 module 5, are valid for Fredholm integral equation of second kind with square integrable kernel. Thus, from theorem 3.6, we have seen that integral equation with square integrable kernel can be associated with integral equation with degenerate kernel, so that the theory of Fredholm alternative can be applied to integral equation with square integrable kernel. Thus, in this chapter 3, we have seen that the Fredholm alternative can be applied to integral equation with degenerate kernel, also to integral equation with continuous kernel, and finally to integral equation with square integrable kernel. So, with this we conclude this module as well as chapter 3.